Okay, so hello everyone. My name is Philippe. I'm a PhD student with Professor Weishi at Laval University. I would like to first acknowledge my co-authors, Dr. Alex Duo, as well as Professor Sophie Larochelle, Professor Younes Mesedek, and of course, Professor Weishi. Today, my talk is about nonlinear photonics in high quality factor chalcogenide microresonators that are directly coupled to silicon waveguides. So a brief outline of my talk. I will start by giving a motivation for co-integration for nonlinear photonics on silicon on insulator. I will then present our fabrication method to achieve high quality factor in chalcogenide microresonators. And I will then move on to present our experimental results. And I will conclude by giving a bit of perspective and our plan for the future regarding this work. So first of all, why co-integration for microcoms and in general for nonlinear photonics? We all know that nonlinear photonics has been mainly supported by fabrication efforts in a lot of different material platforms. That includes amorphous materials like silicon nitride and tantalum pentoxide, but also 3,5 materials like aluminium gallium arsenide, or even materials that have Chi2 nonlinearity like lithium niobate. And there's, of course, a lot more material that are interesting for nonlinear photonics. But silicon and insulator, although silicon has a very high nonlinear index, it's been less leverage, I want to say, for nonlinear photonics because of silicon multiphoton absorption, as well as precarrier absorption and dispersion. It's relatively high thermo-optic coefficient, and also in many cases, the limited quality factor that can be achieved in compact structure. Although I want to mention that very high quality factor can be achieved in multi-mode and relatively bigger structures. So our solution to this is to co-integrate other materials that are not silicon that have good nonlinear properties directly on the silicon insulator substrate. This is a topic that has already been studied to a certain extent, but in general, it's tricky to achieve low loss and compact structures that are required for efficient nonlinear photonics. So the choice of material for this work is chalcogenide. And the reason for that is that they present high linear and nonlinear index. Only Chi3, not Chi2, of course, because this is a glass, so it's amorphous. Also, they're relatively easy to fabricate, at least for co-integration. And they also present low loss over a relatively large transparency window that extends pretty far into the mid-infrared. And they also have very large stimulated scattering gain for either Raman lasing or Brillouin lasing. And more specifically, the composition we choose to study is AS20S80. And this is mainly motivated by the fabrication approach we choose to explore for the co-integration method. So the fabrication approach we choose is a relatively simple one in the fact that we basically only dry etch microtrench waveguides to form the microresonators directly inside the silica cladding. And then these microresonators can be aligned next to the silicon waveguide for evanescent coupling. And here you can see an overview of the process flow. So the first 4 steps are done in foundry. In this case, it's by AMF. And the last 2 steps are done at COPL, and they consist of a thin film deposition as well as a thermal dewetting step. Oops, sorry for that. Okay, so here you can see SEM images of the fabricated microtrench, where you can see the silicon waveguide right next to the relatively large microtrench that will be filled after with chalcogenide glass. And we do that using electron beam evaporation. Here you can see the evaporation chamber with the glass and the substrate holder here that was rotated at 80 RPM. And the deposition rate was 10 angstrom per second. Okay, a bit more detail maybe about the last step in our process, that is thermal dewetting, that is really used to create a smooth, conformal, and flat waveguide inside the microtrench. The basic concept of dewetting is that we break the metastability of the glass by heating it over its glass transition temperature. And doing so, creates a spontaneous reorganization of the glass material around the microtrench. Okay, we can understand the dewatering process of the microtrench into 4 steps. First of all is flattening of the glass, and at some point the glass will meet the substrate and it will create a hole, which we call nucleation, and then this hole will grow through a self-diffusion of the rim that retracts, and more interesting for us, the glass will reflow into the microtrench, leaving a very nice and smooth waveguide. This is what you can see here for the first few images. You can see that we increase the temperature, and at some point, in this case, it's at 240 degrees Celsius. We hold the temperature, and the glass continues to reflow, and we hold that for 2 minutes. Okay, so next, before actually going on to chips, we did the deposition on glass slides, and we did material characterization to have an idea of how the dewatering will affect the material properties. So you can see here EDX, which gives us the composition as the annealing temperatures increased. Here you can see on the left the refractive index, and on the right the thickness that were measured using a prism coupling method. And finally, here you can see Raman spectroscopy curves that gives us an idea about the molecular composition of the glass. And what is really important to notice about these is that there is really a trade-off between achieving like an aggressive dewetting while preventing evaporation of the material, or having actually compositional change, so losing the stoichiometry of the material. And also what is interesting to notice is that according to the Raman curves, it's possible using a very fast annealing that induces dewetting to actually go back to the bulk state of the glass. So that's important for thin films that usually don't have properties that are very close to the bulk state. Okay, what is even more interesting, I think, regarding dewetting, and to me, a strong result of this study is the resulting roughness after dewetting. So that's what you can see here. We used AFM to measure the surface roughness of the glass deposited on the microscope slide, both for 30 seconds and 2 minutes, and they were, yeah. And what you can notice is that as the temperature increases and that we get into the range of temperature that actually induce dewetting, there's a drastic reduction of the surface roughness. And this can be seen here. This is basically the roughness heat map or 3D plot before and after annealing at 240 degrees Celsius. You can see that the roughness is very strongly reduced, and the RMS roughness is actually lower than 20 angstrom, which is exceptional result for this kind of glass. Okay, here you can see the fabricated microresonators, and you can see SEM images on the right of a few different microresonators. You can see the waveguide that is relatively flat and smooth inside the trench, and you can see that there's a pretty good uniformity that was observed over the chip scale. And here you can see a cross section of the fabricated waveguide with the diffused rim. We mentioned maybe that the diffused rim is really regarded as sacrificial material, as we're only interested in the material that actually ends up in the microtrench and really forms a waveguide. Here you can see the surface roughness of the different layers of the waveguide at different stage of the fabrication process. And what you can note is that although the chalcogenide glass has a very low roughness following dewetting, the underlying silica doesn't have as good a roughness, and that's actually what we think is limiting our loss. And the SiO2 cladding is actually a very thin 50 nanometer cladding that we deposited at the end to prevent surface oxidation of the chalcogenide glass. Okay, next we move on to optical measurements. And here you can see the summary of the passive measurements. On the right, you can see a single resonance with a relatively high quality factor of 1.5 million. And you can see multiple quality factors that were measured for the fundamental T, quasi-T mode. that range really between about 1 million and 1.5 million, which is pretty good for integrated chalcogenide photonics. Although it's important to mention that it's not really on par with what's being done in other platforms such as silicon nitride or tantalum pentoxide. Here we also observe higher order modes that had much lower quality factor. And the waveguide was actually very multimode because the index is relatively high at 2.2 and the width of 2 micron means that the waveguide actually supports multiple modes. And this was observed as well in the spectrum. If we look at the transmittance of multiple successive resonances here, we see the avoided mode crossing phenomena where two resonances will kind of march over one another, but never really cross. Okay, and finally, the most interesting part, I guess, of this work is following the fabrication and the relatively good quality factor we achieved, we explored the possibility of using these resonators as either Raman laser or optical parametric oscillators. And you can see here the result. The first thing I want to mention is that the glass photosensitivity as well as the negative thermo-optic coefficient of S20, S80 actually prevented us from having thermal locking and having stable operation and doing more characterization of these microresonators. So what we did is we actually periodically swept the resonance with a pump laser. And what you can see is Raman lasing that was observed in almost all the all the resonance we tested at different power. And the Raman lasing wavelength actually fits pretty well with the theoretical Raman-Kerr. Of course, fits pretty well with the theoretical Raman-Kerr. And on the right, you can see at the single resonance that was pumped at different power. And in addition with the Raman laser lines, you can actually see frequency conversion that are attributed to parametric oscillation. Yeah. Okay, so in conclusion, we demonstrated that co-integration of nonlinear material can achieve sufficiently high quality factor to enable parametric oscillation and Raman lasing. For the specific case of this work where we use chalcogenide, photosensitivity and the overall stability of the glass was a problem for realistic application, let's say. So in our future work, our plan is to test with potentially photosaturation to bring the glass to a photostable state, or to explore other glass composition that don't have this problem. So in conclusion, I want to acknowledge CNC Microsystem for the fabrication subsidy, and CERC and Santé Nord for financial support. So thank you for your attention.